Ever wondered why recurrent neural networks hold such a significant place in the world of deep learning? The answer lies in their unique ability to process sequences of data. This makes them indispensable for tasks that involve sequential inputs, such as natural language processing, speech recognition, and time series prediction. By understanding and leveraging their capabilities, we can unlock new dimensions in the realm of artificial intelligence. So, without further ado, let's delve into the world of recurrent neural networks. To grasp the concept of recurrent neural networks, consider them as a system of interconnected neurons. The beauty of these networks lies in their structure, designed to mimic the human brain, albeit in a simplified form. To understand recurrent neural networks, or RNNs, let's break them down into their fundamental components. The key building block of any RNN is the neuron. Just like in our brains, these artificial neurons take in data, process it, and pass on the output. The magic happens when we start connecting these neurons together, forming a network. An RNN consists of three layers: the input layer, the hidden layer, and the output layer. The input layer is where our raw data enters the network. This could be anything from a string of text, an image, or a series of numbers. Next, the data moves into the hidden layer. This is where the heart of the RNN lies. Unlike traditional neural networks, where data moves in one direction, in an RNN, neurons in the hidden layer have loops. This allows information to circulate within the layer before moving on. In other words, RNNs have a memory of sorts, allowing them to remember previous inputs. Finally, the processed data moves to the output layer, where it is presented in a form that we can interpret. This could be a single number, a set of numbers, or even a complex structure like a sentence. But what directs the flow of information within an RNN? That's where weights and biases come in. Weights determine the importance of different inputs, while biases help the network make correct predictions even when it has little or no input. These two components are adjusted during the learning process to minimize the error in the network's predictions. So there you have it, the structure of an RNN in a nutshell. It's a system of interconnected neurons, divided into layers, with each neuron processing data and passing it on. The unique looping structure of the hidden layer gives RNNs their memory, and the adjustable weights and biases guide the information flow. That's a primer on the structure of recurrent neural networks. But how do these networks process data? The magic of recurrent neural networks lies in their unique data processing mechanism. Imagine a relay race. The data in a recurrent neural network, or RNN, is like a baton passed from one neuron to the next. It all starts at the input layer, where the data is first introduced into the network. This is where our race begins. Now the baton, or our data, is passed to the hidden layer. This is where the real magic happens. Each neuron in the hidden layer processes the data, applying a transformation known as an activation function. This function decides whether the neuron should be activated or not based on the input it receives. It's like the runner deciding how fast to run based on the weight of the baton. Once the data has been processed by the hidden layer, it's passed to the output layer, the final leg of our relay race. But the race doesn't end here. The output is then compared to the expected output, and the difference, or error, is calculated. This is where backpropagation comes into play. Like a coach correcting a runner's technique, backpropagation is used to adjust the weights and biases in the network based on the error. It works backwards from the output layer to the input layer, updating the network to better handle similar data in the future. That's how recurrent neural networks process data. But what makes them so special? Recurrent neural networks are not just another type of neural network, they have some unique features. One of the most significant aspects of recurrent neural networks, or RNNs as they are often abbreviated, is their ability to handle sequential data. This makes them particularly adept at tasks such as language processing and time series prediction. Unlike traditional neural networks, RNNs have loops, allowing information to be passed from one step in the sequence to the next. This gives them a kind of memory, vital for understanding context in a sequence. RNs also employ a technique known as backpropagation for training. This allows them to adjust their internal parameters or weights based on the error of their predictions, thereby learning to make better predictions over time. RNs hold significant potential for a variety of deep learning applications, from natural language processing to music generation and beyond. So that's a quick rundown on recurrent neural networks, a powerful tool in the arsenal of deep learning.